Hello, everybody, and welcome to eCHO episode number 43. In this episode, we're going to be doing a deep dive on FQDN DNS policy, how it works. We're going to see what the knobs and dials are for it. We're going to kind of walk through some experiments. We're going to do a live demo of FQDN policy. I've done that a couple of times this week, and so I'm really looking forward to sharing it with you. As usual, let me know if you're out there. If you're listening or interested in what's happening, just put a comment. I think the comments typically only work if you're in YouTube, I'm realizing. But I'm actually not sure if that's entirely true. This is now being effectively simulcast across a variety of different spaces. So, yeah, welcome. Hey, Chaco, good to see you. Happy Friday to you too. All right, well, let's get into it here. I'm going to jump over and share my desktop. So, our news for the week. Actually, there were a couple of things I wanted to talk about. The first was that we've actually been doing a lot more work with the Cilium Twitter handle. And so if you're not already following the Cilium project on Twitter, you should probably, consider doing that. Because what we've been putting out is actually pretty quality stuff. So when there are new contributors to the Psyllium project, we're actually seeing some notices in the timeline for that. If you want to be notified that there's going to be a new eCHO office hours or what that eCHO office hours will be, that is also a good channel to get notified of those things. And then just kind of keeping track of what's happening with that open source project, the Psyllium. And we're happy to retweet when people are going to make use of it. There's some really great talks making use of cluster mesh. It's actually, Psyllium was just chosen for the Google season of docs and is now accepting applications from technical writers. So if you're interested in doing that, this is going to be really great. It'd be really awesome. You have until April 27th, which is coming right up, 5 days away, to get your application in if that's something that you're interested in participating in. Lots of really great content. So if you're not already following us, you should probably do that. And then the other thing you're going to see us announce, I think it's weekly, but it might be bi-weekly, is every couple of weeks we're going to announce a new newsletter. It used to be that we would cover the news in the beginning of the session, and we're kind of effectively in the way that we're doing it right now. And we decided, I think getting this into a newsletter format like this probably makes a ton of sense. And so now we've actually just made it more publicly available. You can sign up for it. I think the sign up form is here at the bottom. Actually, it says unsubscribe. So probably there's going to be a subscribe if you're not already subscribed. Oh, there it is. Yeah. So here at the bottom, it says, know a friend who needs to be in the know, forward this, and you can sign up here. And that will also just show up in your inbox if that's something you're interested in. Joe, good to see you, Joe. My good friend Joe Talerco is working with me here at Isovalent. Bajaj, good to see you. All right, so good stuff. Lots of interesting things. Chris Nova has been honking around again. I guess less honking, more tonking. This is a really interesting one. I know they were working on it over the weekend, and seem to be putting together a pretty interesting thing here. This is a Linux eBPF backdoor over TCP to spawn reverse shells, get a root exploit, and on prior privileged access. Should be a really interesting project. It'd be really sweet to get Chris on the show again and talk with them about what's happening here. I think this would be a good one to cover. Other things. There's the boot kit, which is what we just talked about. Seriously, please use responsibly. And then eBPF, which is eBPF in hardware, not actually an April Fool's joke. This project now implements most of the eBPF features in FPGA. That's amazing. Noel, good to see you. I come bearing news. Two Ingress Nginx CVEs. Yeah, I would also love to see. I'm sure that Nova will talk about it. I'm sure that there'll be a talk submission somewhere. I'm not sure exactly where that will be. So regardless, you will definitely probably see Nova talk about it. Also, Nova does a lot of live casting. So if you go check out Nova's Twitch, There's probably either recorded sessions where they are already talking about it, or you can participate in a live session and ask questions about it. Nova is super awesome in that way. What are the two Ingress Nginx CVEs? I'm curious about that. I hadn't actually looked into the new ones. So if you as usual, if you want to add things to this news list, if you go to hackmd.io/echo-live, like you see it right down, I always point, it's down there. Yeah, there's a link. You can actually go there, and it will give you access to the nice, and it will give you access to the HackMD, where you can actually put things in here if you'd like. Making sure it's published. Yeah, it's published. So this will be Echo 43, and you can actually add stuff into it, and then we can talk about it. All right. That is the news of the day. Going to be some good stuff. And what else? So eBPF 101, a great 101 conversation talking about Kubernetes observability, supercharging OpenShift with Cilium eBPF. I had a hand in that one. That's pretty exciting. Yeah, lots of good stuff. My good friend Yusuf, one of our solutions architect in France, was part of a podcast recently. Yeah, good stuff. But check it out if you're interested in that stuff. So today we are going to dig into the Psyllium FQDN policy and what it works and how it works and all that good stuff. So I'm looking forward to this one. But the way FQDN policy works, and then we're going to just walk through a policy here real quick, and then we're going to start playing with it. We're going to talk about theory of operation. We're going to get into all of that. Let's see. Bujan says, you got the email. Chaco says, probably not, but I'm not sure what that probably not means. So network policy. So this Cilium network policy that we have in front of us here, what this is going to do is it's going to allow any application with this label set, app equals net, to egress traffic toward anything.k8.intra, and that's going to make more sense as we talk about the test setup. But basically, I'm matching a pattern, so anything.k8.intra, these applications that match this label set will be able to communicate with it. And then down below here, there's a second part of this egress policy. There's two FQDNs, and then there's also two endpoints. And this two endpoints piece does another match. It's allowing egress traffic toward the DNS service within the cluster on port 53 on any protocol. And the rules, and then we have this parser here at the bottom, rules DNS match pattern star. And that basically is a way that increases the visibility into what's actually happening at the DNS layer. So when you have your cluster configured like this, basically you can expect that any application that has this app equals net label set will be able to communicate with anything star.k8.intra and literally nothing else, because there's no other allow rule here. And because we have this egress policy defined, that means that any other traffic that this application would try to make use of will fail, right? It's going to get that implicit deny. But the things that we allow are star.k8.intra and DNS connectivity. And then down below, we have this observability piece, which basically enables us to see or parse the DNS traffic that's going from those applications to the DNS servers within the cluster. And that's going to be super important to us, because effectively what we want is to be able to define policy that allows us to limit access to specific FQDNs. And the way that we implement that in Cilium is that we actually keep a record of the lookup, right? So when an application tries to make a request to echo.k8.intra, for example, the command will use the resolver available within the pod and try to resolve the host name to an IP address. And when it does that, we are actually going to not intercept that traffic, but we're going to observe and parse the result, and the query will emit network events so that you can see those network events going through, leveraging Hubble. And then we'll also make a record in the FQDN cache that maps the FQDN to that IP address. And there are two commands we're going to be using in our testing setup. There's going to be a curl command like this, which is basically just curl, making a connection to this external FQDN, and it's going to do a DNS lookup, and we're going to be able to see that DNS lookup or observe it with Hubble. And then this other command is actually going to make use of a feature, one of my favorite features of curl, which is a feature that allows curl to do local resolution. Now, the interesting difference about these two is that when you do curl http echo.kh.intra -- resolve, and then you provide a line like this, what you're telling curl is, don't do a DNS lookup, use this one instead, right? And so when we make this second command, we'll also be able to observe with Hubble that there will be no DNS lookup. Is this the one about like the snippets? I'm curious, because there was an Nginx. I mean, there continues to be an Nginx bug about being able to implement, arbitrary snippets of stuff. I'm curious if that's the one, because the CVE is basically that you'd be able to, have the permissions that the Nginx controller would have. And so if you're able to do arbitrary snippets, then you're able to effectively run untrusted code in relation to a given ingress definition. And when you do that, then you have the ability to, slurp the certificates and do all kinds of fun stuff. I'm curious that's the one we're looking at. Oh, there's two of them. Boom, boom, boom. Directive injection via annotation. Well, if we have time at the end of this, I'll dig into that. That does sound like fun. I'll go into. So if we run this command, yeah. Now, let's go ahead and just take a look at our cluster, see how we're doing over here. What I've got right here is I've got a cluster that has been created. If I do get nodes, I can see that I have 3 nodes, one control plane node, 2 worker nodes, and they have been configured. We're operating Kubernetes 1.23.3. I've only just stood these up. Let's go ahead and do our Cilium install. Now, there's been some changes to the Psyllium Cli, and I'm actually pretty excited about them. One of the changes that has happened is that as part of the Psyllium Cli, when you do a Psyllium install now, it's actually going to do a Helm template command, and you can see exactly what commands are being used here, right? So I already have kubeproxy in there, so I'm just going to leverage the kubeproxy replacement functionality. There's going to be one operator replica. The service account will be called Cilium. Yeah, all of these pieces are basically what I'm passing with those values that I'm passing into the environment. And then we store those Helm values inside of the kube system namespace in a config map. So I'm going to wait for everything to get deployed here. And while we're waiting for things to get deployed, I'm going to show you a cool thing I just got this week. I'm super excited about it. I'm not sure if you all are aware of it, but I've been really focusing a lot on, in my own personal time, on cubing. And so I've really spent a bunch of time working with different Rubik's Cubes and learning how to do it. And this is my newest one. I'm going to take a second here and do Cilium Hubble enable. We'll turn on our Hubble. And this one is amazing to me because it is still a 3x3, but the difference between this 3x3 and this 3x3 is that this one has a color orientation, right? So every face has a color, and you're solving it by color. And and this one is called a shape mod. And so what's interesting about this is that on each wall, you have a different depth of centerpiece, and you have to like match the centerpiece to the edge that you're creating. Super amazing brain stuff. So here we go, Helm template. This is actually how we're doing the install for Hubble, right? So we're doing the same. We already did the agent install, and now we're going to do a Helm template for the Cilium for Hubble in this environment. All right, so now we got everything installed. We've got everything working here. Let's just do a Cilium status. Looks like everything is up and running. And by default, FQDN policy is enabled. So let's go ahead and just configure one here. So what I'm going to do is I'm going to go ahead, first I'm going to go ahead and do per node. I'm going to use this little bash script, and this bash script does an interesting thing. Mostly it's just kind of makes my life a little easier when I'm trying to interact with like understanding where pods are being deployed and all that good stuff. But basically what it's going to do is it's going to just run, it's going to create a number of pods manually, and it's going to give them, they're going to be based on the Maui line debug image, which has like an echo server running, and it's also got a bunch of like, bash and TCP dump and a bunch of other commands like that. I'm going to set some labels for these pods. So they're going to be called app equals net. We just talked about that a little earlier. And then the pod name will be in there as well. And then the node that is associated will also be in there. So these labels I can use to do different network policies and that sort of stuff. And then down below, I'm actually going to create a service for this as well. And that enables me to give this, I'm also setting the host name and the subdomain for each pod, right? So I'm actually statically scheduling it to the node. So for every node inside of my cluster, I'm going to define the node name field. And that means that I'm going to run this pod on that node. And then I'm actually going to give the host name of that node, of that pod, net, and then the number of whichever instance this is, and then the node on which this thing is going to reside. And then I'm going to do that twice for each node inside of my cluster. And then let's take a look at how that works out. So now, if I do get pods, let's see, I show wide. I have this very interesting characteristic wherein I can actually see I put two pods, net 1 CP01, net 2 CP01, and I put them on the nodes that are in the pod name. This makes it really easy for me to see exactly where I put those nodes. Makes it really easy also for me just to understand like what I have running and what pod I'm connected to and that stuff. Looks like things are, there we go. Waiting for things to get created here. Hey, there we go. Kind of all hit the image at the same time. And so, yeah, so this is actually pretty neat. And then the other thing I really like about this tool is that if I exec in to net 1, they do host name. I can see that I have a host name that maps to a service lookup. That's interesting. Now your question is like, why is that neat? That's neat because I can also use that DNS query to talk to other pods. So if I were to do ping net2 cp02.net, cp01.net, then I can actually get the IP address of cp01 by name. Makes it a lot easier. I don't have to look up the IP addresses. I can just use by name, and that basically builds a DNS entry for me and allows me to interact with it, which is pretty slick in my opinion. So this is a good way of actually like doing same node or cross node interactions by name. And the script that I used is actually is inside of here in the testing environment. Now, let's see, a couple other things I wanted to do here. We've talked about the piece of it. So let's talk a little bit about DNS caching. And then we're going to actually before we do that, let's go ahead and just kick this thing off. We're going to grab this network policy that we created, and I'm going to go ahead and apply that to policy. There is the network policy that we have defined. We have two FQDNs matching on anything star.kh.intra, and then we have that Hubble lookup. So now if I do, let's see, apply dash. I'm going to go ahead and make a forwarder for the node port service that is exposing the Hubble relay service. I'm going to go ahead and let's just take a look at that real quick. So this is the tool that I'm going to use. I'm going to basically create a different node port service that will expose it on a known node port, and that way I can use an environment variable to interact with it. Go apply most kind test H relay. Okay, and now if I do Hubble status, you can see that Hubble is working. And now if I do Hubble observe -f-n default, I'll open another edge here. So now if oh, thank you, Monjudge. I'll check it out. So now I have my Hubble observe happening here at the top. And I have into my net1, actually 01 hash. Let's try our we can see that just like we expected, we can see that if I tried to curl google.com, I did not get a response, right? I'm not able to talk to it. And that's because I don't have a network policy that allows for that. So I'm expecting to see policy denied. But there's some other things that we're seeing in the output here that are also pretty neat, right? So we're also seeing the request. And we're seeing that request across a variety of different subdomains. And this is just the way that DNS works, and it's kind of frustrating, but this is just how it happens. And so because of the search path, because of the default configuration of the resolve.conf in a pod, it's actually going to walk the entire search path and try to resolve the query that I have. So my query was google.com. So the first one it's going to try and do is google.com.default.service.cluster.local. And then it tries service.cluster.local. And then it tries, let's see what else. Google.com.cluster.local. And then it tries google.com.c1.kh.work. And then it actually gets the hit. And it sees there was a response. Google.com is all of these IP addresses and all of these IPv6 addresses. But the traffic was not allowed because there was a network policy that denied it. Now, we were able to see the DNS request. What did we do with that, right? Like we were able to observe that there was a DNS request. Where did we put that information so that it could be relied on in the future? Let's go ahead and take a look at that real quick. So I'm going to jump into the agent where that node is running. So again, right now I'm sitting on net1 CP01, and that means that the FQDN cache that will be used will be stored by that agent. So let's jump into that agent. Do Cilium FQDN cache list. And I can see that there is now a record in here that maps google.com to these IP addresses. If I jump into a different node, let's say the worker node, one of the worker nodes here. Worker 1. I do the same command, Cilium FQDN cache list. I don't see that record. I only see it on the node where the request was made, where we observed it, right? So the Cilium agent is populating this cache, but that is a per node cache. It's not persisted across other nodes. It's an important point because it means that that cache is actually only locally relevant. All right, so we can see a couple of other interesting things about this status, right? We can see the lookup. It's a source type lookup, and that means that we observed it using the agent. And then we can see the FQDN that was actually that resulted, and then we can see a TTL. Now the TTL might be wildly different for the actual record, but inside of Cilium, we keep this record, we observe it, and we keep it around for an hour. And it is also set up to tell you like how long we will keep it around. So by default, the expiration time will be put in here if it's of source type lookup. And then what happens is, like once that expires, then it moves to a different state. Instead of source lookup, it'll be then source connection. And the connection tracking tool, Psyllium eBPF, list, global. This is actually the contract that we have built inside of eBPF, right? So this is the map. This is actually the output of the map of what's actually being seen inside of our contract that is managing inside of eBPF. Once it moves from lookup to source connected, then as long as it's still being used, you would still be able to actually keep that record alive. And this is true of if there's any pod making use of that IP address or one of these IP addresses, then that record will continue to be alive. So what that means is, to make use of FQDN policy, you definitely have to enable some mechanism for us to observe the DNS request and record it. If once we actually record it, we're going to keep that record around for 3,600 minutes by default. Sorry, 3,600 seconds by default. That'd be a really long time. and then, which is an hour. So if we're going to keep that record around for an hour by default, and that's a tunable flag, and we're going to tune it here in a second. At the end of which, as long as if you still had an application behavior, I mean, some applications do this thing where they do a lookup on init, and then they keep the IP addresses that resulted from that lookup for a period of time. And that period of time might be an hour, and that period of time might be effectively until the application gets terminated, but they don't go back and re-resolve to see if that IP address has changed. This is not a great behavior of application code, but sometimes that's actually just how the application code does it. So it will make new connections to that old IP address regardless. And that was actually what I was trying to show with the curl. So if I were to do inside of here, that curl command again, one other thing before I do that, we'll observe F and we're looking at our DNS traffic inside of the default namespace again. Google.com apparently does resolve. We can see that we see that record still. And if I tried to locally resolve it, this is actually when I show you about the curl command. To resolve google.com 804221. You can see that there's no DNS traffic trying to be allowed, right? So I've actually made the call to the FQDN, google.com, that has not been allowed, so that traffic is still being dropped. I can't talk to that IP address. But I'm also not seeing any DNS requests coming in, and that's because I'm actually making use of that curl command to resolve it locally. All right, so that's that part. Now there's a couple things I want to change about the world here. I want to change the timeout inside of FQDN policy, and then I also want to configure my own DNS name. So let's do one of those things first. Let's go ahead and do kubectl edit -n kube system config map core DNS. I'm going to show you a DNS trick inside of core DNS, which I found very useful when checking this out. And that is right here. My intention with the DNS was to have a record that I could change and then the witness or observe that that record had changed so that we could understand that we have control over what happens when it changes. Right. Hosts. There's a load balance. So what this is going to do is going to make use of a plugin inside of core DNS called hosts. And then it's going to populate that plugin with the following information. It's going to set up, it's going to create an A name record for 172.17.02 pointing at echo.kh.intra. And because this is being served from core DNS, that means that any pod inside of the cluster will be able to actually access that host name once it applies. Rollout restart -n kube system deployment core DNS pod -n kube system. So we can see our new core DNS pods are up, and if we were to do curl echo.kh.intra, it works, right? And we can see that the resolved IP address is echo.1 or echo1. And if I go back to my Hubble observe and I make that same command, F and default, curl command. So we're actually seeing that that traffic is being allowed, right? Because we have a network policy that allows me to talk to anything.kh.intra. And we're also able to see that that record is 172.17.02. All right. Now, go ahead and keep that observe up. I'm going to go ahead and edit that one more time. Config map -n kube system for DNS. And I'm going to change the record to show that we can actually change it. This is just what the echo servers are. These are just using the echo server that my friend Mario put up. It's a Docker container. It's running locally on the node. It's just running as a Docker container on the same hypervisor where all of the VMs that I'm actually working with are located. And so they are external to the cluster, and they are they're just echoing traffic. Okay, I'm going to do my rollout restart again. Rollout restart -n kube system deployment core DNS pods -n system. You can see that the core DNS pods are up again. If I jump back into our pod here and I do curl echo.kh.intra, you can see that it now resolves to 172.17.03. Pretty cool. And if I jump back into our that's not the right one. Pods-n system wide grep Cilium. Put back into CP01 here. Cilium FQDN cache list. You can see all kinds of records. Let's see, 172.17.03 and 172.17.02. Then we can see our DNS lookups. We did a google.co, we did google.com. We can see that we're seeing multiple entries for the list. All right. Now, what I want to do is I want to change this value. So let's go ahead and do that. App-n system. Actually, let's do it with the Cilium config now. So Cilium config view. And it looks like the knob I want is not already defined in here. So we'll do Cilium config. Back to our docs here on this side. I want to change the configuration of this. And the way that when we go back to our theory of operation here, it's this value here, 2 FQDNs min TTL. By default, that's an hour. And if I set that to something shorter, like 5 minutes or even 2 minutes, then we'd be able to see something time out. So let's go ahead and try and do that. Config view. We have 2 FQDNs min TTL 120. System. The Cilium pods have already been rolled. You can see that they have an age of 22, 23 seconds, that kind of thing. So now if I jump back into our node here, I'm going to jump back in over here, kubectl exec ti-n system pod name cache. Now the cache should be gone. So if we do Cilium FQDN cache list, oh, it's still there. Hey, that's cool, right? It's actually a cache that's actually persistent. But what I want to do is I want to wipe it out. I don't want it to actually be there because I want to see that the change I made in timing will actually take effect. So let's do Cilium FQDN cache clean. Are you sure? Yes. List, nothing. All right, so we cleaned it out. So now what I want to do is go ahead and do curl echo.infra again. And if I look at the configuration, hey, it worked. So we've made our configuration change. We've set the FQDN timeout to 120 seconds, and we can see that change, right? So now our TTL for this record is 120 seconds, at which time it will move over to a different state. The source will change from lookup to connection. All right. So I'm actually going to keep this on. I'm going to go ahead and change this IP address resolution back to 1702. Real quick, just to prove this out. App-n kube system core DNS. A little bit. And then let's change that to 2. Roll out restart -n kube system deployment coordinates. All right. So here's what we got so far. So we have gone ahead and we've configured we've reconfigured the cache to hold the record for 2 minutes and then let it expire. We can see that cache is still populated. We can see when it will expire, which should be pretty soon. We have gone ahead and changed the record. So if we were to go ahead and do, so even from here, actually, yeah, if we were to do this curl command that we had before, we're going to see that it resolves to 172.17.02. So if I do my cache lookup again, I can see that one of them has moved to connection state. The other one is sitting there in a new record. So we're going to keep that one around for 2 minutes. Now in connection state, we're still able to communicate with that old record. We're kind of modeling that behavior, that kind of interesting behavior that applications do, where it may actually hold the IP address and try to continue to connect to it, even though the resolution of that host has changed. So if we do our lookup on that pod again, or on that node, on that host name, we're seeing that the resolution of that host name has changed. I do host echo.kh.intra. I see that there's only one resolved name or IP address for it, and that is 172.17.02. But I can still connect to it manually on that old IP address by doing manual resolution. And it will keep that around in the lookup table until nothing is connected to it for a period of time, and then it will age out using contract. So pretty cool stuff. That's actually how FQDN policy works. Those are the 2 phases for it. That's actually how it relies. So you have this FQDN cache piece, and then you also have the ability to age things out and to interact with them in that way. So a couple other interesting things about this before it's all over. I wanted to bring up the other the other pod running inside of this node. So we'll do kubectl exec ti-n net1 net2 is what I want. cp01 bash. I'm on a completely different pod, right? Now this pod has this endpoint over here. This is the endpoint that is related to this pod here on the bottom. And we could see that if we wanted to validate that, we could do kubectl get CEP. Because we can see that 624 is net1 CP01. And net2 CP01 is endpoint number 1. Okay. All right. No, the FQDN cache actually only clears it for the node that we're on, because the cache itself is only on a specific node. So Cilium FQDN cache can only clear the cache that is local to that node, and the cache is not persisted across nodes. It is persisted across reboots, but not across nodes. All right. So, all right, so we have our endpoint. So that's what I was saying. So this endpoint, 624, can actually make use of it. We can see that policy still there. Actually, you can see that both of them have aged out. Now, one thing that's neat is if I go ahead and make that same lookup again, we're going to be able to see that it changes back to lookup. So you can move back and forth between those two source states from lookup to connection. As soon as it sees a new lookup, it's going to effectively reset the expiration time for another hour. So it's not going to accidentally time out. It's going to wait for that TTL to expire, and then it will actually remove the record, but it will keep it in connection state as long as it's still being used. And we can see that connection has timed out, right? So I no longer have the 172.03 resolution. So if I were to try and do that command here, I would get denied. I would get a policy drop. I will observe and default. See, this is my policy drop because I no longer have a mapping of 172.17.03 to echo.kh.intra. Neat stuff. Now there is actually one other thing I wanted to show, which is that when you have that FQDN cache and it's specific to that node, then other nodes can make use of that same FQDN cache. And this is going to get into the detail of like how we make use of that cache, right? So if you think about this, this is going to be kind of similar to a reverse lookup. We need to be able to understand that the FQDN you're trying to communicate with is mapped to an IP address. And we need to be able to determine that not only by host name, but also by IP address, right? And that means that like if you cache that entry and your application is trying to connect to that IP address that was the IP address that this host resolved to initially, then you're actually just connecting by IP address, and we need to be able to ensure that FQDN policy will allow that traffic even if that behavior has changed. So I wanted to show you this because in my opinion, this is actually really pretty clear. So I do my curl command. I can see my connections going back and forth between 172.17.02, and it's talking to echo 1, which is what I'm expecting. And there's that record. And you can see that every time I resolve it, that expiration time is being updated. But if I go over to another pod on the same node, I still need to be able to look. I'm going to assume that both of these pods started about the same time, did an init, got the IP address that it was going to resolve to, and are now trying to make new connections to that old IP address, right? So in this example, I'm going to go ahead and do the same curl command, curl echo.kh.intra. I'm going to do that resolve thing, echo.kh.intra, colon 80, where you want to connect to, and then the IP address, 172.17.02. Now, what's interesting about this is the pod on the right here is going to try and make a connection to that IP address without doing any resolve. I'm going to stop all traffic. And we're going to go ahead and so when this connection happens, we're not going to see any DNS requests. We don't have any record of this endpoint in here either. What do you think will happen? It allowed the connection. And that's true because the way that this has to work is that for you to be able to make use for that application behavior where the application keeps the resolved IP address around for a period of time that may be more than the actual TTL for that DNS record, we need to be able to determine that you're making a connection to an IP address that we have a mapping for. And so this is what I mean by it's kind of like a reverse lookup, right? So your connection going to that IP address, we are able to map, we're able to reverse look up. That connection is going to 172.17.02. That is mapped to echo.kh.intra. There is a network policy that allows all of the pods in the default namespace right now to make connections to echo.kh.intra. And thus I have to allow this traffic, which in my mind is kind of mind-blowing. When I first heard about FQDN policy and Cilium, I was like, how are they going to do that? But now that I really dig into the detail of it and I understand more about that model, it's actually really impressive how it's working. Now, if that other pod does make a lookup, we're still going to get, we're also going to be able to see the lookup for that pod. All right. I think that covers everything I wanted to show you. We talked about the different states when it moves from lookup to connection. When it moves, you can move back and forth between those states. In the connection state, as long as there's something trying to make connections to that old IP address, we'll keep it around. We won't remove it until it actually gets wiped out or not in use by the. It's determined that it hasn't been used for some period of time in contract, and the contract line ages out, and that's when we would remove that record from the FQDN cache. Let's go back to our notes here and see if there was anything else I wanted to talk about. We talked about the different stages. Oh, one other thing that we could talk about is like the configuration defaults. The one that we adjusted in this session was actually the 2 FQDNs min-TTL. But there are some other values, things like limits, the ability to ensure that we only keep so many IP addresses per host name, the idle connection grace period timeout, the max deferred connection deletes. All of these things are ways to control the behavior of FQDN policy or FQDN policy inside of Cilium. So I've actually put notes in here about the DNS configuration that I used and like how that actually works. So you can go ahead and set that up. And these are just, again, like 2 Docker containers listening on port 80 and 443. Our test environment, 1 control plane node, 2 workers, just did a Cilium install and a Cilium Hubble enable. This is the script to create all of the containers. And then here are our testing methodology, how we went about testing this. And if you want to play with this, you can also explore these things. So we got about 8 minutes left before I want to take off for the day, but let's take a look what happens to other record types like a CNAME or a multiple A record. So we actually kind of already saw what happens on multiple A records, right? Which is that if we go ahead and make a connection to curl google.com, we're going to get the traffic denied, of course, but we are going to see the record. And so google.com resolves to multiple IP addresses. So we're able to see that up here at the top. What happens if we do a CNAME, though? That's a good question. Can I make a CNAME with the host plugin? Let's find out. Nope, it only does A, and PTR records. Okay, but I think I already have an FQDN. I think I already have a CNAME in here, which might work. So let's just take a look. I think in my lab environment, I've got one set up, but let's just jump over there and take a look and see what happens. Open tab. Let's see. I'm sending that to CP01. And that record is host foo.apps.c1.k8.work. Cool. And then there, okay, so yeah. So here's what I've got set up in the lab environment. I've got an HA proxy instance, and I've got DNS. And DNS is actually configured in such a way that I will send star.apps.c1.k8.work to the HA proxy instance, which will then resolve it. is that a CNAME? I think it is, right? Because it's CNAME for API.c1 div. So let's go ahead and manipulate some stuff here. That's the front end for it. And here's the back ends. So I want to forward C1 ingress HTTP. I want to change the IP addresses to 172.17.02. I'll also put in 03, and we'll just load balance across the two of them for that one record. Didn't change anything else about the line. Should be good to go. On source, mode TCP. SFLU. Backend C1 ingress HTTP, another server named CP01C1KH.work was already defined on line 170. What are you talking about? Didn't change any names. Oh, I see. So this will be called echo1.c1. Work. There we go. I should be able to restart. Yeah, much happier. Now if I do host, actually if I do curl, even from out here, if I do curl echo.kh.work, kind of expected that to work. Oh, fine. Well, looks like my HA proxy foo is not going to be happy with me today. Sure, that's totally unrelated. I think that's just an arbitrary field. What if I jump back over here? If I do curl go dot c1 apps dot c1 okay, work. I jump into my pod. Oh, am I wrong about that? No, that's still 192.168.201.1, which is the HA proxy service. Yeah, it's kicking my butt. All right, well, I'll figure that out some other time. But I'm pretty sure it would just keep it. But my guess is it would be much the same thing. Exactly. We're trying to resolve the A name. Not only that would be cached. That's my understanding as well. Yeah, that's factory. All right. Well, thank you all so much for attending. I hope that this was useful. I learned a lot in digging into it. I thought this was actually a pretty cool thing to kind of dig into. Actually, you know what? I'm being silly. I don't have to. I can actually prove it out. So if I do host foo.apps c1.k8.work, I'm actually getting a lookup here, right? And then if I go back into my node here up at the top, FQDN cache list. Okay, so that's actually mapping to the IP address. Exactly. Yeah. So it's doing the full lookup. It's looking at it all the way. It's looking at it all the way down. All right. Yeah, I don't know where my head was at. I was like, I was overthinking the problem. Story of my life, man. Story of my life. Overthinking the problem. Anyway. Yeah, Rio, it's a big challenge for sure. Like, I think you hear me say this pretty frequently, but this stuff is complicated. Like everybody, I think we work real hard to make it simple, but at the end of the day, it's still pretty tough. Anyway, thank you all so much for attending, and I hope that this was useful to you. And if it was useful to you, feel free to give me a shout out on Twitter. Let me know what you think. If you have any questions or anything I didn't cover that you would like to see covered better, do let me know. I hope that you enjoyed it, like I said, and I will see you all next time. Thank you so much. Enjoy your wonderful weekends. All right. Bye.